Good morning, everyone. My name is Sanjay Shah, and I look at oil and gas from a Deloitte technology and transformation perspective. And welcome to this session. Very interesting session on the overall thought process of supply chain, logistics, and operational excellence. This is focusing more around the AI and digital transformation. As you will know that in the current context, AI is the only thing that is being discussed when you talk about technology. And we have got a very talented panel here. People who are working on the ground on AI and ML. In fact, they are very interesting sessions. One on the upstream side, where about 300 wells data is analyzed and looked at from predicting flows. The other is on the refinery side, where entire modeling has been done to look at giveaways and how to reduce giveaways, and maybe a bottom line impact of more than 5 crores has come in. The third is on the LPG forecasting, and the fourth from Dipti is from a safety perspective. So these are the 4 sessions, and we will be very keeping it around 15 minutes per session. We'll start from Arindam, who comes from ONGC and who has done a brilliant work around how to look at forecast of production based on various parameters. So Arindam, over to you in terms of talking about it.
Good afternoon, everyone. I'm Arindam from ONGC. So my presentation is on AI and ML usage to get more insight on the sandstone completion. Okay, so that's the brief of my presentation. I'll introduce my topic, then I'll go into some theory aspects and what are the applications of the data. So the photo up there is of a hydraulic fracturing operation we did in 3 wells of a same well pad. So I move forward. So that's the theme of the research. We have collated reservoir data, completion data, frac data, as well as production data. Data of more than 300 wells were collated, and a variety of designs were considered for the analysis. Self-organizing data mapping was performed, and the key concepts include clustering and feature detection. So we use 2 layers. One is an input layer, and the other is an output layer. So that's the basic architecture of a self-organizing map. So as you can see, there's an input layer and output layer. So for the house, I would say that we have considered 2 bins, and based on the input and the weightage of the input towards the output, it self-organizes itself. So that's the basic idea of what my study was about. So how we have come across the weightages for which it would assign itself, I'll come to that. So for bin modeling, I have considered 2 bins. One is a reservoir bin, the other is a completion bin. So the parameters that I have considered in a reservoir bin are pore pressure, permeability, porosity, net to gross ratio, and water saturation. For completion bin, I have used the data that I get in a fracturing job, like pad volume which we design, clean gel with sand, the number of perf holes open, the average proppant concentration, total sand pumped, and tubing size. Now for the house, I'm in hydraulic fracturing engineer. So hydraulic fracturing, just as we know, is the process where we pump fluid and proppant inside the reservoir to generate more production. So there is quite uncertainty in the reservoir data that we get, upon which we design and go for the actual execution of job. But when we actually execute the job, we generate a lot of data. So my study is based on generating a feedback loop where we can assume better with AI and ML the parameters upon designing during a hydraulic fracturing job. So this is a brief of the data sets that I have used. For confidentiality purpose, I have kept the well names as well 1 like that, and these are the various parameters that I have used. Now on the weightages of the parameters. Now what does the bin results show? Now, first we plotted porosity via the production data. That's the actual production data. So we came to the conclusion that porosity has a significant impact on the production, that is the actual post HF production gain. There have been instances where above a minimum average value of porosity, we get good production gain post HF. Next, that the data was collated was regarding permeability. So normally fracturing operation is executed where there is a limited amount of permeability. So upon collation of data, we came to the conclusion that upon a minimum permeability, we are getting good production gain post HF. Next is pore pressure versus production. Now for the house, pore pressure is a very critical parameter that we is a reservoir related parameter which is calculated and mostly is based on statistical analysis. So an interesting analysis came up that higher the pore pressure, the better is our production gain. It has a significant impact on how we look at fracturing. I will come to that later. Next, the parameter that I looked at is net versus gross ratio via production data. So for the house, in every like wherever we perforate for oil and gas, so geologically there is a gross pay, and of that gross pay, a limited amount bears hydrocarbon. So that is designated as a net pay. So that this is a critical parameter that we use for our analysis purpose. So this parameter via production was collated. So we have come to the conclusion that higher is the net to gross ratio, the better is the production gain, though there are certain aberrations in the way we look at the data. Next is the water saturation versus production. So geologically, every formation that we perforate for oil and gas bears some amount of water. Now, our candidate for our candidate well selection for fracturing, water saturation is a critical parameter because post fracturing the amount of water ingress is more, the chances of water ingress is more, so we need to limit the data. So this is also a critical parameter which we came across during our research, and as you can see from the data, the lower the water saturation, mostly it has given rise to higher production gain. Then we looked at the cases where there was geologically lesser water saturation, but it still gave rise to a better production gain. We collated these aberrations with the geological input that we have, and we came to the conclusion that not all water saturation does flow out of the reservoir post frac. So that is a geological phenomena, and some insights on it were obtained when we were analyzing the data. Next, I come on the frac parameters which came in the study itself. So for the house, so hydraulic fracturing process starts like this, that first we pump a limited amount of volume which doesn't bear any sand particle inside the formation from the surface. So that is called a pad volume. Post pad volume, where a fracture is created in subsurface, we post the propant volume. Propant volume is placed in the fracture, and then we flush out the all the propant, slurry laden propant. So that's about the hydraulic fracturing process. So we studied how much clean gel with sand we are using in the our HF job. So we came to the conclusion that lesser the clean gel with sand we are using, or rather the lesser the pad volume we are using, more or less we are getting the better result. Now, number of open holes versus production. For the house, what does number of open holes mean? So say example, there is a 4-meter interval. Now for perforation of the holes, normally we perforate at 18 shots per meter, meaning in every meter of interval subsurface, 18 holes are shorted. But not all holes would be open at the subsurface. That we get this data from a minifrac injection test that we do at subsurface. So we collected that data also. We had that data, and we found out that the more the number of open holes that we get during the uh, this subsurface, the higher are the chances of production gain post HF. And the more the number of open holes also has a direct bearing on the pad volume that we need to use, and a clean gel with sand that we need to use. So more open holes in turn leads to a lower pad volume as well as lesser clean gel with sand. So all the three parameters at the end of the day have with data analysis I am finding out that has a direct bearing on the production gain that we are observing. Now, an important parameter is the average propellant concentration versus production data. Now, what is the average propellant concentration? So, in a hydraulic fracturing job, normally, as I had mentioned, we pump a small volume of fluid into the subsurface. After that, we start pumping slurry laden sand. So normally we pump from a lower propellant stage and we move to a higher propellant stage. Such for simplicity, say suppose 1 pound per added gallon of sand, we start at that propellant concentration and we move towards 8 or 9 ppa concentration. The higher the concentration that we can move during a hydraulic fracturing job, the better are our chances of oil gain. So we have found out that on that aspect, we normally calculate the average propellant concentration. So normally we have seen that a better average propellant concentration leads to a better production gain. Okay. Next is the total sand pumped versus production. So this is a very, very reservoir related phenomenon, because some reservoirs might need higher tonnage of sand to be pumped and some reservoirs might need lower tonnage of sand to be pumped. So we had a lot of data on it. What we found out is that after increasing concentration sand pumped beyond a certain limit, it doesn't give rise to any appreciable gain in production after a point. So it's very important, this parameter is very important from a cost perspective. So if this data is fed in the bin, so we can calculate based on the historical data of the reservoir what should be the ideal sand size for a particular job. Next is a tubing size versus production. Now that's a very critical component as far as the completion is concerned, because tubing size after all determines the completion strategy of a well. For everyone in the house, tubing size is the production tubing from which the oil and gas flows. So tubing size determines at what rate, or rather the maximum rate I can pump my fracturing job. So for me to pump at higher rates, I need a bigger tubing size. Or if I need to pump at a limited rate, a normal tubing size should do. So normally in our fields, our tubing size is 2.7 by 8 inch. But in some cases we have observed that even higher sized tubings also give rise to much higher outcomes. Now the summary part, what the data analysis gave me in summary and the bin results. So it says that increase in pore pressure by only 100 psi results in production gain of 6%. It should be viewed in reverse. Reservoir at subsurface are mostly in depletion drive. So at what point in the life of the reservoir we do the hydraulic fracturing job is very essential as far as HF success is concerned. Next, in summary, I realized that mere increase in porosity by even 0.1% results in substantial production gain. So these are the reservoir parts. In as far as average propellant concentration is concerned, so we have seen that a mere zero point 0.4 ppg, though zero point 0.4 ppg is a like quite a amount as far as average propellant concentration is concerned, it has given a rise to a production gain of 7%. And regarding the job size, which is the critical part, a very cost intensive part, because on it our opex depends how much sand we pump. So we have seen that optimum job size results in better production gain. So this is the data that we have collated, and we have sort of some self-organizing map of which we are using right now, so as to cut down our cost and increase our operational excellence.
Thanks,
Thank you.
Arindam. A big round of applause for Arindam. Straight away impacting production, use of technology. Thank you so much on sticking on time as well. So the next session is on real-time product quality prediction. This is again a very interesting presentation given by Mr. Sri Kumar and Mr. Saurabh Gupta. So request you all to talk about it. And it has got straight away bottom line impact. So over to you.
Good afternoon, everyone sitting over here. First of all, I would like to thank our IEW and the panel members for selecting this paper and giving an opportunity for making this use case to be presented in front of you. Having said myself, D. Sri Kumar, heading the IS Digital and Optimization in BPCL Kochi Refinery, and I have my colleague Mr. Saurav Gupta, Chief Manager Digital. He will be joining with me after some time. So the topic over here is, so the topic for this presentation is real-time product quality prediction and control through AI-driven machine learning integrated with APC system. So this will be the flow of the presentation. So we'll be just touching about what are all the various digital initiatives which has been done in Kochi Refinery. What is our business challenge? What is this AI-based learning which we are bringing to your notice, and how it is helping us in our refinery segment. So having said this, BPCL Kochi Refinery as well as our entire BPCL have started our journey on implementing various digital technologies quite some time before. So some of the key things which is displayed over here, the digital twins have been implemented, AI/ML, which we will be talking about sometime shortly, the virtual reality and the augmented reality, which is for our skill development, competencies development. The smart data center has been introduced. Now for this technology to run, it requires a strong platform infrastructure. So we have introduced a spine leaf, latest technology, reducing the carbon footprint in this, and ODR, operations driven reliability. This is for taking care of our reliability of our equipments. The people tracking, RTLS systems are there. The complete unit, the PDPP complex, PetChem unit is completely digitally connected. So everything can be done from the shop floor, not from the office itself. People, when they are going for the rounds, they can connect to the systems always. Then we use drones for major turnarounds, for safety surveillance, and for other aspects, as well as CCTV for our surveillance, the perimeter surveillance. Robotic process automations have been implemented in many of the business functions, finance, CPO, procurement, and so on, as well as IoT sensors. And not only that, our MES system, which is our prime system for our refining manufacturing execution system, which is for the advanced process control, and all other historians are in place. Having said this, this is the team behind this solution who has conceived it, who has implemented this AI/ML journey in Kochi Refinery. So coming back to this APC, why this AI/ML journey has started? APC, as you all know, advanced process control, it is to develop the property or quality inferential and control it in the real-time basis. However, it is somewhat a 2 decades old system which is having certain constraints, not moving into the new digital interventions and the advancement of technology, what is happening. Hence, we have to go to the next level of the journey from APC. So that is why this AI/ML machine learning has come into picture. and also some inaccurate predictions it cannot happen in the for nonlinear systems, and it is not able to adapt to the rising business demands. So many business demands keeps on coming for us, and we have to cater to that need. However, there will be a lot of business challenge because of inaccuracy of spec product can come in, the upset in downstream units can take place, too much dependability on the laboratory analysis as far as APC systems are concerned. So how do we move on this? So to overcome this, the team has come out with a complete solution. So they have identified what all the historical data are required over a period of time. Info Plus 21 is our historian. So 6 years data has been collected. It has been computed with an high power computational systems, and using the Python and MATLAB, we have implemented this particular solution. So our journey started somewhere from 22 initially. Having getting the confidence, there were many ML programs have been developed in-house, which has been done in a very short time, and so many machine learning algorithms have been generated and we have implemented. So this comprises of in PFCCU, propylene content prediction in PFCCU, PRU, C3 bottom, CDU3 AGO prediction, CDU2 AGO prediction, and latest is CDU3 video D95 prediction. Having said this, all these use cases, some of the things which my colleague Mr. Saurav Gupta will touch upon, he will take you through the journey, how we have gone through it, and what all the various benefits we have gathered in this. So thank you, and I'll welcome Mr. Saurav Gupta over here.
Thank you, sir, and good afternoon, all. So I will cover the first case, which is propylene purity prediction. This is actually the first case which we deployed successfully in the year 2022, to be precise, December 2022. So let's see the problem statement. So propylene actually is a product which is coming out of the PFCCU PRU unit. It is having a percentage purity as an specification. We have to maintain minimum 99.6% of the purity, which means that anything less than 99.6 is off spec, and anything more than 99.6 is a case of quality giveaway. We are having an analyzer which is not at all accurate. We are also having APC inferential, but it is hovering between 95 to 101. So, and you know, it's being the purity, it cannot cross more than 100, right? So this was a business challenge for us, and with that we started carrying out the ML modeling. So what we exactly did is that we studied the plant in detail, and we could identify the 17 number of parameters which could potentially affect the quality of the propylene in the real time, you know. And then after that we pulled 2 years of historical data from IP21. We are using ASPAN IP21 as an historian, where the minute wise minute data is getting stored. We pulled 2 years of data. We carried out basic cleaning in the Excel, and then we carried out detailed cleaning using the MATLAB software. And then we tried various machine learning algorithms, we tried deep learning algorithms, and then we could come out with the Gaussian process algorithm, which gave us the best result. So this is actually the output from the MATLAB software for the regression that we carried out. I'm not sure whether it's visible or not, but for the Gaussian process algorithm, it's showing that we could achieve the RMSE, root mean square error, of 0.089, which is actually very less, and we could do it with the R square value of 0.77. Once the model is ready, that's kind of an easy job, that we believe that has come out of the experience. The next big challenge is to deploy the model in the real time, that too at the refinery level, you know. And when we are saying deploying in the real time, means your prediction should reach up to the DCS level, and then the APC should be able to read that prediction and then should be able to take action based on that. Means what we are talking about is a closed loop, and doing this entirely in-house was a very big challenge for us. To be precise, we struggled after the model development. We struggled almost for 7 to 8 months just to deploy the model. So we could come out with this unique architecture, where this MATLAB model we are converting into an application through a compiler, and this application we are running on a standalone machine using the help of a MATLAB compiler runtime. My real-time plant data from the IP21 is, we are fetching it into an Excel, and then we are pushing it to the application, and then the output is again coming to a new Excel, and we are running a Python continuously every minute, and this Python is actually pushing this prediction to the SQL, where the SQL query is actually pushing this data back to IP21, and finally we are able to write it to the DCS level. And I'm proud to say that this whole architecture has been conceptualized, developed, and deployed successfully entirely by the BPCL Kochi refinery in-house team. Let's talk about the accuracy. So this particular model, which we did in December 2022, this is 99.9% accurate. My orange line is ML prediction and my blue line is the lab result. And on one fine day, my this lab result actually deviated a lot from the prediction. Actually, it became off spec. If you see, it's went below 99.6, which is my this limit. And then based on the we again saw the condition. We based on the confidence level on the ML model, we challenged the data. We asked the plant people to send the recheck sample, and the recheck result exactly matched with the ML prediction. Let's see case 2. So in July last year, July 2024, the requirement was there to create an algorithm to create a model for the D95 prediction. So CDU3 AGO is atmospheric gas oil, basically the diesel which is going to the secondary unit for the sulfur treatment, and D95 is a distillation property, that basically the temperature required to recover 95% of the product by volume. For this we started the modeling. The problem statement was that this gas oil is having a this D95 specification of maximum 362. Again, anything more than 362 is an off spec, and anything less than 362 is a case of quality giveaway. So what we did, we studied the plant and we could come out with the 30 number of the plant parameters which could potentially affect the quality of the gas oil. And we consider 1.5 years of training data. We could come up with a machine learning model with an R square value of 0.78. And this is the graph where again the orange line is a prediction and the blue line is a lab result. And you can see that the orange line is actually following the blue line in tandem. And this accuracy of this prediction, ML prediction, was much more superior than the APC inferential, and that is why the APC people integrated it with the APC people start taking it as a control variable inside their domain. Let's talk about the benefit post deployment. We actually deployed it at the July end. So in the month of July, when the ML was not available, 355.5 was the average lab result of the D95 for CDU3 gas oil. You please note the specification is 362. The APC value was 347.8. This means that for the July month there was an error of 7.7 degree between the APC inferential versus the actual lab result. Post deployment in the month of August, the lab value was 359.1. ML prediction was 360.3. So if you see, ML versus lab error was only 1.2, but again for the August month, APC versus lab error was 7.4. So if you just compare APC inferential versus ML inferential, ML is actually 85% more accurate than the APC inferential. If you compare July and August month, there is an improvement of 3.6 degree, which actually in terms of diesel yield improvement, it comes out to be 0.65%, and in terms of money, it comes out to be rupees 4 crores on an annual basis. Uh, Similar to CDU3 AGO, we could immediately within in August first week we could deploy CDU2 HGO D95 prediction model. The case was quite similar, only the plant was different. So again, we studied the plant. We could have come out with a model with an R square value of 0.86, which was much better than the R square what we got in the CDU3 AGO case. Again, this is an orange and blue line, and this is actually a test data. So this is the data which the model has not seen, and you can see the accuracy from the graph itself. Let's talk about the benefit of the CDU2 HGO model. So again, for the July month, when the ML was not available, the APC versus lab error was 2.5 degree. If you note, my lab average value for the entire July month was 365.2, which means that against the spec of 362, this was a case of off spec. Post ML deployment, my ML average prediction was 363 and the lab result was 362.7. So if you see APC versus ML for the August month, my ML is 0.4 and APC error was 4, which means that ML is actually 90% more accurate than the APC inferential. Also from the July to August month, there is an improvement of 2.6 degree in terms of off-spec reduction. If I talk about the overall benefit of all these ML deployments, we are having an improved prediction accuracy. Because of that, we are able to control the quality in a better fashion by integrating it with the APC. Better quality control means lesser giveaway reduction, means you are having an improved yield and then better margins. Not only that, because of the better control, the number of cases of off-spec has gone down, which means that we are having a criteria of reliability improvement. So this is leading to the enhancement of the reliability for the secondary unit catalyst life. Not only that, because our accuracy of the inferentials have gone up, ML inferentials, so our confidence level has gone up, and this means that our dependability on the laboratory has gone down, which means that less number of samples, less number of recheck samples we are sending to the laboratory, which means that more time saving, better personal effectiveness, and then better manpower utilization. With this, I will just summarize. So what we actually did is that we identified a real business problem in the refinery level. We could identify AI-based machine learning as the solution to the problem. We developed, successfully deployed the solution with a unique architecture. Not only that, this entirely project, all these projects have been done in-house without any external support. And since the project has been done in-house, the cost involved is zero, which theoretically means that there is a case of infinite IRR. We believe that this is a real example of digital transformation. With this, I end our presentation. Thank you very much.
Thank you so much. A big round of applause to both Mr. Kumar and Mr. Saurabh Gupta. It's fantastic presentation having a bottom line impact. The next presentation is by Mr. Praveen Kumar, CGMIS of IOCL, which is on enhancing of LPG purchase forecasting. Altogether different topic vis-a-vis the technical aspects that we saw. So over to you.
Thank you everybody for turning up at this hour. I am Praveen Kumar. I am Chief General Manager, and in Indian Oil. I am responsible for the customer relationship initiatives, and this case that we will be presenting is a step in that direction. So let me just see if it's working. Yeah. I okay. So before I start off with the presentation, just to put things in context, we'll be answering 3 questions in this. Why we have done what we have done, first part. Second is obviously the what part, what have we done, and the question is how we have done. So the key takeaways will follow. Let me just do a simple mind exercise with you. Okay. Now let's imagine there is a mother of 2 children who is preparing breakfast for her sons in the morning at 6 o'clock, and the bus is about to come at, let's say, 7 o'clock. She is rushing to the kitchen, and suddenly she finds that the LPG fuel that she is working on is run out of it. It's a strange situation to be. And similarly, if you have planned a party for your friends at the in the home, and right in the middle of your cooking exercise, you find that you are running out of this LPG fuel. It's definitely not a pleasant thing to be in. And to understand, put things in perspective again, for our customer base of 15 crore Indian Oil customers, 9.8 crore customers actually have a single bottle connection, which means 62% of them are having this. And when they land in this kind of a situation, what will happen is you'll be scrambling around asking your neighbor, what can I borrow your cylinder? Probably they will have a different connection from a different vendor, and things like that will follow. So that was a motivation to undertake this exercise. And what we have done is we have tried to use AI/ML techniques to build a improve the customer experience and the engagement in the process, right? In Indian Oil, what we have done is we have undertaken a CRM initiative way back in 16-17 under the name of Project EPIC. EPIC stands for our electronic platform for Indian Oil customers. Now, this platform that we have set up is today, as we can claim, is the largest CBIL installation program in the world. We have more than 15 crore customers, LPG customers on this platform. There are retail customers, and in terms of loyalty customers, we have around 3.8 crore loyalty customers on this platform. So this is probably one of the largest installation that we are looking at. The database size of 120 terabytes, this actually forms the core of the backbone of our customer engagement platform. Going forward, this just provides a brief overview of the expanse of our platform. We have 13,000 LPG distributors, 419 lube distributors, some 40,000 retail outlets who are connected to this and engaging on this platform, to around 3 crore customers who fill fuel from our outlets every day. So this is a huge platform that we are talking about. This is an architectural layout of the solution that we have. The core of the platform is the Oracle Siebel solution that runs on this, right? Now, there are various initiatives which are part of this platform. SDMS CRM for our retail, LPG lines of businesses. We have the mobility initiatives, the campaign management initiatives. Our eKYC solution also extends this platform, plus the analytics and other components that are there. Our loyalty program is the extra reward loyalty program, which I mentioned, as I mentioned, is for 300.8 crore customers and all these channel partners that are integrated on this platform. We have revamped our mobile strategy. We have created 3 different segments of mobile applications. One is called the Indian Oil one is the major application for our retail customers. Indian Oil for Business is the partner application, and Empower One we call the application for our field sales force, right? So just putting things in perspective, we have 15.8 crore LPG customers with us, and out of that 9.5 are on single bottle connection. Now for them, any disruption in the services is a challenge. It's something that we can throw their small life out of gear. So how do we make an impact in this area? This was the motivation for us to take this initiative. Now we have various channels of booking from our customers use various channels to book cylinders from us. This is through either WhatsApp, through missed call option. We have the option of booking through the mobile phone or the portal, right? Now going forward, it's a very normal thing. When you're running through the days of your normal days of your life, you will forget when you have booked the last time and when probably you will exhaust your existing cylinders, right? So how do we actually improve this through digital intervention? This was the motivation for this. So what we did was we tried to not that we short of data. We have a huge database, 150 terabytes of data. We decided to develop a model for each analyzing each customer and understanding what his booking pattern has been for the last, let's say, 6 bookings. So for the customer base we are talking about, this will actually spread to something like 2 years going backward. So we have 2 years of data. You analyze the customer's buying pattern, rather booking pattern, and then we can come up with a solution, expected, or what you call expectancy, when he will be actually running out of his existing refill, for which we can immediately prompt him to make a booking, right? So this was the genesis of that, and this is what we did. What we did was we analyzed his bookings for the last 6 months, try to determine when his next refill is due, and we nudge him, send an SMS and ask him to make a refill booking. So this is just a kind of a recap slide where we have various categories putting AI in perspective, and we are talking about machine learning, where we actually use data to develop models which can predict. Going forward, yeah, let me come to the actual methodology for data preparation. What we talked about is 15 crore customers, past 2 years of data. We analyzed them, past refill booking pattern which was available, and we tried to identify the parameters which are significant in our modeling effort, right? Like what are the demographical patterns? Either you are a rural customer, urban customer. What are the connection time? Definitely, it's a very important parameter. SBC connection or a DBC connection, and what is the impact of seasons that we have. So these were the significant parameters that we could uh, extract these as a feature for our model building exercise. Now we ran this, we implemented this ML algorithms, regression models, random forest, and gradient boosting. We got the best performance results from HD Boost, which we actually deployed into production. Right now, if you see what we did, the process is, what we do is we look at the buying pattern. We try to predict the forecast when the next refill is due, taking into the consideration what is the backlog that the dealer is running and the time to deliver. We send out an SMS. Let's say there is a backlog of 2 days at the dealer's end, and it takes another 2 days to deliver a cylinder to a particular customer. So 4 days in advance, we are sending out the SMS. It's a nudge that you book with a URL to actually, or a missed call you can do to the initiate a booking, and with that he gets a notification or a confirmation that the booking is done. So this has been implemented, put into production, and what we have found out is the results are very encouraging, right? Uh, to just present the architecture of the solution, this is the architecture. We have our transactional database, which is the Oracle Siebel CRM. We extract the data daily from this for all the customers who are doing the booking. We take it on another database where we actually do the feature selection, and we try to run the machine learning algorithms. Again, this is generated a new data set database we populate, wherein when and for whom, which customers we have to send out a new notification. This is done on a daily basis, and once this is available in the morning, we send out a notification to all these customers, right? So spend just some few minutes on this slide. So this is a dashboard that we use to monitor the performance of our machine learning system that we have developed. If you look at it, we have sent out, on an average day, we are sending out around 6 lakhs and 6.3 lakhs messages every day to customers for nudging them, right? Now this, if you see, around 7.63% of the customers actually respond back. Based on the notifications that they have got, they will actually respond with the booking notifications. And subsequently, over a period of time, over the last 1.5 years that we have run, 17.4 customers, percentage of the customers have utilized the services. So this is the spread. If you can see, this has been a great learning experience for us also, and we keep to improving this model further. In fact, one of the best testimonials that we actually got from our customers was this. What he essentially says is, he was pleasantly surprised to receive a notification, and incidentally he ran out of the cylinder that very same day, and he actually was querying that, do we actually use a machine learning model or not? And probably that was the best proof that this thing is working. So this was a pleasant and a motivating experience for us, and we hope that this actually sets us path on building more innovative solutions for our customers. Thank you.
Thank you so much. A big round of applause to solve customer problems. So fantastic presentation. Now we move into the operational aspects. We talked about the business dimension. So the next presentation is by Ms. Dipti on robotics and AI use for safe energy inspection. So which is an extremely important area in the oil and gas segment. So over to you, Dipti.
Thank you so much. So, good afternoon, everyone. My name is Deepthi. I'm from Baker Hughes, and Baker Hughes is a company, energy technology company, which takes energy forward with robotics and artificial intelligence for safe energy inspections. Okay, the problem arises when Baker Hughes, which is an energy technology company, as I said before, um, has to invest millions of dollars in repetitive inspections for like these are manual inspections which are carried out in confined spaces, which poses significant risks of security to the FSCs, the personals who do these manual inspections. To overcome these hurdles, Baker Hughes is attempting to create a platform which helps in doing these repetitive inspections equipped with multiple sensors on robots, and which would be able to work autonomously. This would be a fleet of robots which would be managed by a platform to do autonomous inspections in hazardous regions. So I would be happy to say that BH would be the first OEM to offer such autonomous inspection solutions, and we would be able to deliver full service from missions definitions and creation to robots and integration in the fleet, data analysis, and technical delivery. So I would just give a brief overview of how these inspections can be performed. The first one is the human operator. The second is when fixed sensors are integrated in the plant. So these fixed sensors offer continuous monitoring, but with the use of robots equipped with advanced sensors and AI capabilities, we can achieve wider coverage and flexibility over the whole inspection domain. So the first package that we provide is the internal package where we have sensors mounted onto a machine or in a plant, and they offer continuous monitoring. And the second solution is when we have a fleet of robots and drones with advanced sensors which are deployed onto a plant, industrial plant, or in ATEX certified settings. Um, Along with the integrating drones for aerial visualization, we can also get data from satellite images. So you can see on the right, there's uh, Copernicus 5P Stropome satellite, which provides methane emissions, daily images of the methane emissions for a particular area. So we can integrate the data from this satellite over the platform to manage the emissions for a particular plant. Okay. So this platform, the robotic inspection platform provided by Baker Hughes, has 7 components. The first one is Python toolkit, which allows integration of robots onto the platform. So this toolkit would consist of drivers which are implemented specifically for the robots, drones, or sensors to be integrated into the platform. There is the second component, which is a fleet manager. This component would allow uh, the operator to autonomously manage the fleet and deploy them to do autonomous inspections in the whole plant. Then there's the third component, which is fleet management, where the operator can review how the fleet is functioning, get the data, and they can basically modify if they want to like send some robots to a particular inspection area, and so on. Then there's the plugin deployer. So the platform has plugins which are plug and play components. So these plug and play components are AI models where the data can be passed as an input, any type of data, provided the model is present in the repository, in the template repository, which I'm going to sign next. Um, so the data can be passed in this plugin, and the output can be visualized in the platform to show how the inspection is performing, or to detect anomalies, or do some predictions on the input data. Then there's the template repository. This template repository gives an overview of the AI models that we would have in the platform, which can be integrated with the inspections that the robot is carrying out. So the robot would autonomously go to a particular inspection site as instructed by the operator, and carry out the inspection. The data would be passed through a plugin, and the output from the plugin would be provided in the platform for future use by the operators. So before performing any inspections, there's always a risk because we are using robots, and we don't know if the inspections would be correct or not. So to simulate these inspections, we have robotic simulator. So the robots that we provide have the simulators on board, and the inspections that the instructions that we program into the robot are run through the simulator to see how the robot would perform in the actual plant environment. Then there's the data manager. So the data manager would just store the inspection data and show it in the format that is required by the platform. So this data can be stored in the cloud, or um, in on-prem deployments, the data can be stored on a physical machine. Okay. So the robots that we use currently is shown in the top right corner. There's the first robot, which is Taorob, which is a crawler robot, has a robotic arm which can be used for doing specific inspections on the plant machines. The second one is the animal robot, which is ATEX certified, can be used efficiently in stair climbing scenarios, and in hazardous environments, since it can work in high temperature ranges. And it can mount up to 10 kgs of payload. So we can fit in advanced sensors onto these robots to perform the inspections. Then the third one is from X Robotics, similar to what I told you about the first robots. Um, the output from a particular plugin is shown in the image on the bottom right corner. So we have a comprehensive report of how inspection is performed, like what are the inspection points, then images of, or relevant data for that inspection, and the output. This is an overview of the Fleet Manager platform that BH is developing. The first image shows a fleet of robots along with sensors. We can integrate different kinds of robots, drones, as well as sensors into the platform, and we see an overview of the fleet health. The second image on the right shows data storage capabilities of the platform. So this data can be stored, as I said, on cloud or on-prem, but the data can be visualized like the original data before the inspections, before the AI model is applied, can be showed in the platform. On the bottom left, we have a particular asset analysis. So there's an inspection point which is identifying duplex filter. So this is a thermal image where the duplex filter would show like the filter would be hot when the filter is working, or cold when it is not. So we do this kind of analysis and visualize it in the platform. Then on the bottom right, we have fleet health information of how many missions have been performed, how many were there autonomous missions, and how many were successful, how many failed, and so on. So the way in which we deploy this platform is through a plugin deployer, a fleet management system, a mission planner, which would help in autonomous mission planning, and a mission simulator, which I explained before. So we develop this platform in 3 environments. The first one is the tech environment, which analyzes how these features should be implemented. The dev environment, where the developer tests these features. Quality environment, which tests the features in a testing environment. And then in the client environment, we have the storage. As you can see, it can be on-prem or on the cloud, and the fleet management system, where we can see a comprehensive overview of the fleet, a mission simulator to simulate the missions, and a mission planner to autonomously plan the mission. We also have a plugin registry, a tech toolkit, which would allow plugins to be deployed autonomously into the platform when they have been added from the backend. So these plugins are actually AI models which perform analysis on the input that we want. So whenever we want to add a plugin, these plugins are actually independent of each other, independent of each other's environments, and can be containerized and deployed anywhere where the client wants. So these are some advanced sensors that can be mounted on the robot. There's the sniffer sensor, the OGI sensors for gas analysis, then the thermal cameras, LiDAR cameras, and high FPS cameras for vibration analysis to sense if the machines are working well, and acoustic sensors to monitor the health of a particular machine. So this is the capabilities of the plugins that I discussed before. So these are the AI models, which are actually object detection models or custom models developed by CV specialists. So the data is collected by sensors, ATEX certified sensors, to be actually deployed in the industrial environment. And it is passed through these plugins, and the visualization is done as shown in the images. Okay. So this is the tracking capability of the platform, where we show the flanges have been detected into the video that the fleet agent is performing. Okay, we just have this video. I would like to say that we have pilot projects deployed onto some plants where we are getting real-time data, then doing AI asset analysis, providing inspection solutions, and there are some clients which are interested in our project. So if you have interest in this solution, please contact me offline. Okay, thank you so much.
Thanks. A big round of applause. Thank you so much. Very interesting discussions, and with this, we would close this session. And in case anyone has queries for the various panelists, you are free to kind of interact after this session. Thank you so much.